Buenos días a todos a este webinar. Les quiero dar la bienvenida a todos y especialmente al doctor Frank Lodge de la Universidad de California. Les quiero inicialmente presentar un poco sobre lo que estamos haciendo en el Tecnológico de Monterrey en cuanto al tema del agua. Desde hace el 2008 estamos iniciando el Centro del Agua. Es una iniciativa que junto con la Fundación FEMSA y el Banco Interamericano de Desarrollo, con la misión de contribuir a la sostenibilidad del recurso hídrico en la región a través de investigación, innovación, transferencia de conocimiento, capacitación y soporte a la toma de decisiones. En el 2013 iniciamos el núcleo estratégico de decisiones como una parte, un avance en este proceso. Y en el 2019 iniciamos la iniciativa sobre economía circular del agua FEMSA, cuyo objetivo es fomentar acciones de colaboración enfocadas al desarrollo estratégico del nexo agua-energía. Tenemos en el Tecnológico de Monterrey un grupo de enfoque de investigación estratégica en ciencia y tecnología del agua, en temas de procesos hidrológicos, procesos de tratamiento de aguas residuales, análisis de química del agua y nanotecnología, procesos ambientales, geoprocesos ambientales enfocados al impacto ambiental y esta cátedra que ya mencioné en economía circular del agua FEMSA. Como parte de esta iniciativa, invitamos al Dr. Frank Lodge de la Universidad de California, Davis, a ser parte de esta iniciativa como profesor distinguido del Tecnológico de Monterrey. El profesor Lodge es actualmente director del Centro para Eficiencia y Eficiencia de Energía Agua y profesor del Departamento de Ingeniería Civil y Ambiental de la Universidad de California, Davis. Él empezó su carrera estudiando el tema del agua, del tratamiento de agua y de aguas residuales y ha desarrollado un gran interés entre la relación entre agua, energía y salud. Defiende la realización de investigaciones fundamentales para avanzar en el conocimiento y el desarrollo y despliegue de las tecnologías y políticas públicas que mejoran la calidad ambiental y la eficiencia en el consumo de los recursos. Sus investigaciones se centran en las implicaciones de los sistemas naturales y de ingeniería para la energía y la salud, el diseño de sistemas y tecnologías sostenibles, la seguridad y la privacidad de los datos y el emprendimiento. El doctor tiene un doctorado en Ingeniería Civil y Ambiental de la Universidad de California en Davis.
Thank you, Jorgen.
Well, hi Frank. How are you doing?
Good.
I would like that you share us our presentation, and I thank you very much for accepting our invitation.
You're welcome. I'm just getting my screen ready. And Jorgen, you can see my screen?
Yeah.
Okay. Good morning, everyone. So I'm going to talk to you today about a topic that's fairly new in the water sector that really focuses on the relationship between water and energy. And I'm going to give you a brief overview before we get started with the actual presentation today. So I am a professor in the Department of Civil and Environmental Engineering at the University of California, Davis. And I'm also the director of the Center for Water Energy Efficiency on the UC Davis campus. So this is a brief introductory slide to our center. Our primary mission is to advance the management of solutions for integrated savings of water and energy resources. And shown on the right is a series of circles that represent all the different activities that we're active in that are required for us to accomplish our mission. So our overall goal is to kind of help advance the management of water systems in the 21st century. And that has brought in a lot of areas of activity that historically have not been part of water systems. So a good example might be data security and privacy. When I was younger and starting my career in water, we never dealt with data security and privacy, and nowadays we do quite a bit of work in that area. So today I'm going to talk to you about a series of several projects that focus on kind of subsets of the activities that our center is involved in. So the primary goal of my webinar today is to discuss current kind of case studies that represent opportunities that represent the ability to shift energy electric load, specifically electricity electric load, through water demand management in different sectors of our economy. So the residential, commercial, industrial, and irrigation sectors. And I'll go through and define here very quickly what's meant by energy load shifting and water demand management. So we'll start with an overview of the challenges of renewable energy integration into electric grids. And when I refer to electric grids, with the exception of the last thing I'll talk about, which is microgrids, when I refer to electric grids, these are large-scale grids like on the scale of a state or a country. And these electric grids are the power lines that transmit electricity from the source of generation ultimately to the end users like you and I in our houses, or to commercial buildings, or different types of industries. So I'll spend some time talking about renewable energy integration and the challenges it represents or poses, and then ultimately how renewable energy integration into the grid really motivates the need to shift electric load. And then from there, I'll talk about 4 different opportunities, possibly 3, depending on how time permits, but opportunities in the water sector to have the water sector shift their electric loads in response to the needs of the electric grid. Okay, so shown here on the y-axis, so this axis here, is the load and net load expressed in megawatts as a function of time over the course of a single day. So this is just a typical day. And the purple line here represents the load that's placed on the electric grid. So the load placed on the electric grid is all the uses of electricity in houses, commercial buildings, industry, collectively, if you add all that up, this is the load that's placed on the grid that the grid then needs to provide. Now the blue, the light blue line, or the light green line, is the amount of electricity that's generated on this day. And I should point out all this information is specific to the electric grid in the state of California. So this light green line is the amount of electricity that's generated through wind, which is a renewable source. The lighter lime green line, shown right here, is the amount of electricity put on the grid from solar. And if you take the amount of electricity generated from solar and wind and subtract it from the load, you end up with a curve which represents the net load, which is shown here in the light blue. The net load is the amount of electricity that needs to be generated by generally non-renewable sources. So this would be coal-fired power plants, natural gas power plants, possibly nuclear power plants, and then hydroelectric are the primary sources of generating electricity to meet this net load. But the main point you should take away here is that the net load looks very different than the actual load. And the net load is what our power plants need to provide in order to ensure all of us have electricity in our businesses or at our homes. Now, this is a representation, just shown here again is megawatts on the y-axis expressed as a function of hours over the course of a day. And this is a typical day. And what's shown here is the net load over time, over about 8 years. And so in 2012, this is the actual net load in the state of California. So this is for the state of California electric grid. And over time, we've seen this, people oftentimes refer to this as a duck curve, D-U-C-K, because it's supposed to look like a duck. This is the head of the duck, this is the neck. And over time, what we've observed is that the belly of the deck has gotten bigger and bigger. And this is because of the integration of renewable energy into our statewide electric grid. And the problem, which I will elaborate on here in a moment, but the problem is that as this belly gets deeper and deeper, it's very hard for the statewide electricity grid to provide electricity during this ramping period right here. And this ramping period occurs around 4 o'clock in the afternoon and extends until about 8 o'clock at night. And this ramping period represents when all of us get home from work and turn on lights and start to cook and do other things like that. And it also represents the time period where renewable energy generally stops being generated. So solar no longer is producing electricity because the sun is going down, and the wind turbines are not producing electricity because the wind has died down. So this ramping period occurs for 2 reasons: people coming home and the renewable energy going offline. This ramping period is incredibly hard to meet because you have to have non-renewable sources of energy on the grid waiting to turn on during this period of time so you can meet this period here. And if the belly of the duck gets too deep, the amount of electricity you need on the grid so you can meet this ramp is greater than the amount of electricity being used. And in that case, you create a very dangerous situation. So if you have more energy than you have demand, you have excess energy, that's when you start to blow out power lines and, create problems at your house with your circuit breakers and things like that. So excess energy is very bad. So what is done, this is a busy schematic, but I'll spend a little time discussing this. So this is a cartoon, if you would like to call it that, of the electric power grid in the state of California and the decisions that people need to make. So over here in this box is all the different sources of demand for electricity. So you have industries, you have the water sector, you have agriculture, and you have residential houses or commercial buildings. They all create electricity demand, which is shown over here as the energy load. You also have distributed generation of electricity. So this is through wind and solar. So this is showing, the schematic down on the bottom left is showing the electricity that's generated through renewable sources. Hold on, my screen I just have a technical detail I'm gonna have to fix here. Excuse me just for a second. Sorry, my screen is frozen. So this is one of the challenges from working at home because I have no IT support to help fix this problem.
Professor Locke, is something that we can help?
I don't think so. It's, I can't advance my slides.
We're seeing the slides and that they are advancing. Maybe
They are advancing.
Yes, they are.
Oh, okay. Then my screen on my side is completely frozen.
Yeah. We're seeing two methods of shifting energy demand in the water sector.
Yeah, Monica, can you go ahead and discontinue sharing with me real quick, and then
I can also, I have the presentation, Frank, I can also share it.
yeah, let's just see real quick if you could just stop. If Monica, if you could just take the screen from me.
Sure.
Real quick.
There is Professor Jürgen. If you have the PowerPoint presentation, maybe you can start sharing.
Do you see the presentation?
Yes, we can see the presentation.
Yeah.
Professor Locke, can you see the presentation?
No, I just still see my frozen screen.
Okay. Okay, don't worry. We can take a 5 minutes break. Maybe this can be fixed if you leave the meeting and then come back again, if
Okay.
it's possible. I don't know if you're how is your computer? Yes.
Yeah, I'm sorry about this. Okay, I will do that right now.
Yes, thank you. Professor Jürgen, maybe you can while Professor launches, it's going to reconnect himself. Maybe you can tell us something about the water center in Tec de Monterrey.
Okay. Actually, so okay, it's unfrozen. So let me.
Let's try again.
Yep.
If there's, I can go. If there's the problem still going on, I will disconnect Facebook Live. That would be easier. There are not so many people in the in Facebook Live.
Okay. All right. So coming back to this, so this is the worldview of the operators that operate the statewide electric grid. So in this box right here, you have demands, and this is the demand of electricity from these different sources. You also have distributed generation of electricity. So this is through wind and solar. If you add these two together, you end up with the net load or net demand, which is shown over here, which is very similar to the slide I just showed you previously. On this side of the screen over here, you have different sources of producing energy. So here I have shown wind and solar, but also then this could be a coal-fired power plant or a natural gas power plant, a nuclear power plant. And these different sources produce energy that goes onto the grid. And the energy that is produced needs to match the net demand. If these two don't match, then what happens is we enter into a process called curtailment, where some of this electricity is shed off the grid so that this electricity profile matches the net demand. These two have to match each other because you do not want excess electricity on the grid. That'll cause things to break. And you don't want less energy on the grid because then you'll have brownouts or blackouts. What we're finding in the state of California is that curtailment is happening more and more often as we put more and more renewable sources of energy on the grid. Why curtailment is bad is that we are not using that electricity. So in the state of California, when we curtail electricity from our grid, what we're doing is we're giving it to another entity, and the most common entity we give it to is the state of Arizona. And what's surprising is that we don't charge them for that electricity, and we don't give it to them for free. We actually pay them to take our excess electricity. So curtailment not only comes at a cost to the state of California, it also is bad because we are not using the renewable energy that we're generating. We're actually paying someone to take it. So it makes it very challenging for us to add additional renewable energy to our electric grid because we don't have the ability to use it when it's generated. So, so that's the big challenge with the integration of renewable energy into electric grids. One thing I just want to note here, and I think this is self-evident, but this is kind of a critical piece to my presentation today, is that it's a recognition that water systems, so shown here is a potable water system, so a water system to provide drinking water. So there's a number of activities that are associated with a potable water system. So you have to extract it. So say you need to pump it from the ground, you need to convey it and store it and then treat it. And then ultimately you have to, once treated, you have to send it through a distribution system to an end user. All of these activities use energy. So if the end user is sitting down here at the very bottom, and if they were to modify how they use water, that would then have an influence on the electricity that's needed to get them that water. So water demand management is an activity that influences the timing of when water is used by the end user and how it saves energy, or it doesn't save energy, but how it shifts the electric demand is that it then influences the electricity needed for all these activities upstream. There's also an effect which is not shown in this slide, but if you were to take this and put it in reverse down here, that would represent the activities that are needed for wastewater treatment, and each of those activities would have an energy associated with it. So an end user, by shifting when you use water, you are then actually shifting the use of electricity for all these activities, as well as all the activities associated with wastewater, which are not shown here. On the right-hand side is a map of the state of California, and they have broken the state out into roughly 10 hydrologic zones. And these names here, North Coast, Sacramento River, these are the names of the hydraulic zones. Shown in bold is the amount of energy that's required for it, and that's expressed in kilowatt hours per acre foot of water. That's the amount of energy that's required for the water system and the wastewater system. And shown parenthetically down below is the amount of energy that's required just for the water system. So you can see quite a diversity throughout the state in reference to the amount of energy that's needed for water systems and wastewater systems. And you'll have to take my word for this, but these numbers are fairly large as well. So a considerable amount of energy is used in water systems in the state of California. If you look at statewide, about 20% of our electricity use as a state is associated with water and wastewater systems. So that's a very large amount of electricity. So the question, the focus of this webinar is to look at how we might shift when we use water in an effort to shift our electricity use in water and wastewater systems. And the potential amount of electricity that we could shift is 20% of the overall state's electricity use, which is quite large. Now, there's two different ways that water systems can shift their electricity demand. So shown here in this top bar right here, this is the water demand. It's a cartoon representing a concept, but here is water demand as a function of time over the course of a day. So, so this is the water demand. So there's high water demand and low water demand and high again. And in a normal water system, the energy use matches the water demand. So when there's less water demand, there's less energy that's needed for the water system to source the water, convey it, store it, treat it, and then send it to the customer. And when there's a high water demand, there's a higher energy use. And generally, water systems of this type operate with pumps to move the water from its source to its final location. And that's primarily, pumping is primarily the user of electricity in water systems. Now, shown here in the middle bar is a representation of one way to disconnect the relationship between water use and energy use. And so here we have water demand, but now you'll see that energy demand looks very different. The water system has effectively shifted when they use energy, but they have not shifted their water demand at all. And how they have done that is they have not only put in pumps, but the primary thing that they have put in is storage. So they pump water during certain times of the day and store it to use during high demand periods. And by storing water, they can shift their electricity profile so it no longer matches their water demand profile. So this is through water storage, and the water storage would be within a water utility, not within a residential house or a commercial building. The storage is generally very big and within the water system. And the final way, and so I am not going to discuss this method of shifting electric load today. What I am going to focus on is this bottom bar, which is shifting the water demand. And by shifting the water demand, you are shifting the energy demand. So this concept, translated in very simple terms, could be represented with an example, which would be the water utility telling all of its residents to water during certain times of the day. So generally we water at night when it's cool, and the water utility might say, well, we want you now all to water in the middle of the day between 1 and 4, so that we can shift our electric demand so that we have a higher demand for electricity during those time periods. Those time periods happen to correspond to when we have large amounts of renewable energy on the grid. And right now, we're concerned that we might have surplus electricity on the grid from renewable energy sources. Therefore, we would like you to shift how you use your water. That's the topic of today's webinar. So I'm going to go through 4 case studies, if time permits. I'll certainly get through three case studies. But these are case studies that illustrate different ways that water agencies can help encourage water customers to shift when they use water. And again, by shifting water, they are shifting the electricity needed for that water, which is helping the integration of renewable energy into the electric grid. So the first example I will give you is an ongoing project that we have with the East Bay Municipal Utility District, which is in the San Francisco, Berkeley area of California. It's a very large water utility. And they are actively attempting to practice water demand management through what they refer to as water reports. So these are reports that they provide to the water customers. And this is an example of a water report. So this is, and this report is intended to help provide information to water customers to modify their behavior. And the idea is fairly simple. So if water utilities can communicate directly with the users of their water, they can begin to help communicate what they want their customers to do. So this is the welcome letter that is provided to each of the customers within East Bay Municipal Utility District service territory. It says, welcome, you're part of this new program where we're gonna provide you information about your water use, and we're gonna encourage you to do certain types of activities, and I'll show you a few examples. But what's illustrated down here, these 3 ideas, so they're these 3 items, so they're gonna help people understand their near real-time water use, how you compare with other people, and then they're going to give you an opportunity to sign up for alerts. So this is what the water utility has chosen to message around, but these messages could be around anything. So what I'm going to illustrate to you is some of the messages they sent, and then at the end of this particular case study, I will show you the effectiveness of this type of messaging. So this is a message about their real-time water use. So this message is sent to a particular water user. So this, we could pretend this is not true, but we can pretend this is my house. And I get this message, but none of you on the webinar would see this information. So this is customized information to me. And shown here is the amount of water on the y-axis expressed as a function of time over a given day. And it's showing my actual water use. Now you can imagine that if our goal is to shift water use into certain times of the day, I can use this type of information to encourage the water customer, in this case me, to use water, say, during this time of the day, and to discourage water use during other times of the day. The messaging also provides information of how you compare to people like you. And you know, the definition of like you is, I can get into at some point if you'd like. But I know this is a little hard to see, but this right here is this account. So this is me. This is people, this is the average of people like me. And this is the best person in that group of people like me. So it's comparing me to the average, to the best person. And the intent here is that if I can understand how I'm doing relative to others like me and the best person, this information might begin to motivate me to change my behavior in some way. This is a frowny face, if you can't tell. If I were this person, I would have a big happy face. And if I were this person, I would have a somewhat happy face. So what they have found is this type of messaging is very effective because inherently we are all very competitive, just being humans, and we like to be good at whatever we do. So this type of messaging, it has proven to be very effective in encouraging people to modify their behavior. And the one other example here, they do send alerts. And so this is just an example of one type of alert that they send. And this is a leak alert. So they send this alert in two different ways. Over here on the left is just this right here is just a very simple message that they will send saying, hey, we think you have a leak. It's estimated to be at 609 gallons per hour, 609 gallons. It's happened over 23 hours and it's about a 27 gallon per hour leak. You can also show leaks by looking at the water use over the course of a day. And you could say this blue bar here is how much water that you normally use. This is how much water we anticipate is being lost through leaks, which is shown here on orange. If you add up all this over the course of a day, then you get these numbers over here. So two different ways to message. And again, it's just an example of an alert, and they've chosen here to use leaks as an alert. So East Bay Municipal Utility District rolled this water report software out to all their customers. They have about 300,000 customers in the Bay Area in California. And they've done this as part of a pilot program to understand whether or not it's effective. And so the graph I'll show you next is data that was obtained as part of this project. This is an ongoing project. This data is about 4 days old. But what I want to illustrate to you here, one of the bars is not showing up for some reason. But right around this period right here, if I were to draw a vertical line down, this is when they made the portal active. And so what's shown here is water use, and it's expressed on a 100 cubic foot basis. So this is 1.2 is 1.2 times 100 cubic feet. We call it CCF. It's really confusing, I know. This is how we deal with water in California in terms of water volumes, but it's 100 cubic feet of water. And shown here is different days over the course of the study that we've collected data from so far. So right around here is when this water report was rolled out. Shown in red is a group of people who did not receive the water report, and shown in blue are the people that did receive the water report. And what you'll see is once the report was rolled out, you see a separation between the red and blue bars or lines, which indicates that the water report is helping reduce water use. And that difference is on average somewhere between 4 and 6%. So by messaging water customers information about what water utilities would like water customers to do, you can begin to get responses from your water customers that make the water customers shift their water demand. And through this process, you can have messaging that encourages water customers to shift when they use water so that you can modify how the water utility uses electricity to help the water utility use electricity when there's quite a bit of renewable energy on the statewide electric grid. And why that's so important is that that keeps that renewable energy on our grid so that we don't have to pay someone else to take it off our grid. And the example I gave was the state of Arizona. The next example that of a case study that I just like to highlight here in terms of an opportunity for helping encourage water demand management as a way to shift electric load. The example is of high resolution hydraulic modeling and how that can help identify specific customers to target specific, to help identify specific customers to target in your messaging to help get some sort of response. And the response we'd really like is for the water customers to shift when they use water, to shift when electricity is needed. So shown here is the water use for different sectors within, in this case, this is the East Bay Municipal Utility District. They have residential indoor water use, irrigation, commercial, industrial, public, and institutional. And then the darker green line is the total water use. So this is the water used in million gallons, expressed as a function of time over the course of a day. And the main point here is that different water customers use water at different amounts and at different times throughout the course of a day. So you can begin just looking at a graph like this to understand this messaging I just showed you, these water reports. You might not want to message all your customers around their water use. You might want to target a specific class of customers that either uses a lot of water or that uses a lot of water during a certain time of the day. All this data is not from a hydraulic model. This is just data, empirical data that's collected from the water utility. What hydraulic models can help do, and this is an animated feature here, is this is a pump within a particular area of the East Bay Mud Service Territory. And this pump is providing water to each of these dots is a connection where water is taken off. So you can think of these dots as either a residential house or as a commercial building or an industry. And the hydraulic model is developing a forecast of how this water is moving throughout the water system. And the red represents the dots that receive a lot of water from this pump. And the dark blue represents areas within the water system that receive none of the water from this pump. So if your goal is to shift the use of electricity for this pump, you can then begin to use this model to specifically target your messaging just to the customers that are represented in red on this schematic here. So the hydraulic model, through high resolution modeling of how water moves through the water system, can now help target that messaging to the actual customers that are going to have the greatest impact on electric load shifting for a particular asset. In this case, the asset was an individual pump. But you can define how you target water customers based on multiple assets and a whole range of criteria. And why this has become important is while messaging through social media or electronic means like emails, web portal access, well, that's low cost and easy to do, and you can target an entire city. The uptake rate of that messaging generally is very low. So I might provide the city of Monterey a web portal for everyone to look at, but of their water use and message around that. But the actual number of people that look at it generally is very low. It's on the order of anywhere from 5 to 10% is how many people within a community would look at that. Whereas if you send everyone a physical mailer that comes in the mail, generally, well, the uptake rate is 100% because everyone gets it. And generally a very large number of people will read that is what we have found. And so, but mailing things comes at a cost. So having information like this of where to target those mailings is highly effective at helping reduce the cost of a program you might roll out, messaging around how water customers might use their water in different ways. The third example I'd like to talk through is irrigation scheduling. And so I think that this is somewhat intuitive to understand, but if you schedule when irrigation occurs, this isn't a direct way to manage water demand by scheduling when irrigation occurs and does not occur. So this was a project that we worked on with the Molten Miguel Water District, which is in Southern California. It's right next to the city of Los Angeles. And this is a representation shown here of their water system, their water system that receives recycled water. So they are collecting their wastewater, treating it to a very high degree, putting it back not into the potable water system, but into a recycled water system. And they are sending that water out to irrigation customers. And so this is their service territory. And each of these little green dots and gold dots are accounts that receive some of this recycled water, and they use it for irrigation. So these P's here are parks, but all these other green dots are other types of users that are receiving recycled water and using it for irrigation purposes. So they have quite a few users of recycled water that are using this water exclusively for irrigation. So this is a great example of an opportunity to really target all these different customers to encourage them to time their irrigation to correspond to some criteria that the water agency wants to achieve. In this case, what we're really interested in is shifting the timing of their irrigation to shift the electric load within the water system. Shown here is the total amount of water used across all accounts, and this is expressed as gallons per minute as a function of time over the course of a typical day. And the hashed lines, the hashed part here is the existing demand, and then the part shown in gray is the shift, is the demand once shifted. So what we have done is we've encouraged people to shift their irrigation out of this time period and to shift it over to this time period. And you can see that the amount of water that we've shifted is actually quite small. And I will show you some results of shifting a small amount of water. And these results then would be considerably greater if we had encouraged water agencies to shift more water. What we found, the challenge is that most of the very large water users in the Molten Miguel service territory that use recycled water are golf courses, and it's very hard for them to water in the middle of the day when people are playing golf. And currently they water mostly at night. So our ability to shift a large amount of water in the service territory was limited by a few very large water users that did not have the ability to shift water. But for those that did, we shifted that water. And what I'll show you here is two schematics to illustrate this. So the first schematic is what we did is we went through and we took their existing recycled water system and we optimized it to maximize the amount of water that's stored in reservoirs and in containers to help shift electric load. And then on top of that, then we shifted demand by reaching out and encouraging people to modify their irrigation timing. So this line right here is the results of total water pumped, total energy consumed, and total greenhouse gas emissions in million metric tons of CO2 equivalents of optimizing the water system but not shifting their demand. So by just by helping change the operation of their system to encourage storage during certain times of the day, we were able to reduce the total amount of water pumped by 24%. We reduced the energy used by 17.97%, and that corresponded to about a 22% reduction in GHG emissions. The GHG emissions are associated with this electricity that we reduced. Now, if we reduce irrigation demand, if we shift irrigation demand, we then achieve these numbers here, which are greater than just simply optimizing their system around storage. So we achieved a huge amount of savings in both water, energy, and GHG emissions by timing when irrigation occurs within the recycled water system. For the sake of time, I will skip this slide. And I want to go on to the fourth case study. And I put this one in because this is not really an example of water demand management, but it is a nice example of how you can think outside the box when you recognize the value of water demand management and helping shift electric loads. This is a nice case study of how to think outside the box, where if you can't shift water demand, maybe you can do some other things to still achieve the same outcome that you're trying to get, which is shifting the time that a water agency uses electricity off the electric grid. So this example is not with a potable water system, it's with a wastewater system. And in this wastewater system, we built and then installed a microgrid to help modify when electricity is pulled off of the statewide electric grid and used to treat wastewater. So this project that we completed was at the Laguna Wastewater Treatment Plant. This wastewater treatment plant treats water in Santa Rosa. So Santa Rosa is a city that's right next to Napa Valley. Napa Valley is where we produce a lot of wine in California. So this is in the wine country. The wastewater treatment plant serves 230,000 customers roughly. So it's a quite large wastewater treatment plant. And it treats on average about 17.5 million gallons of water per day. I know this is busy, but this is really intended for those of you that are interested in wastewater. So this is the unit operations and unit processes that are in place at the wastewater treatment plant. So wastewater enters here, passes through screens, grit removal, primary clarification. So all the boxes in gray are typical of a wastewater treatment plant in terms of unit operations and unit processes that are necessary to treat wastewater. All of these have some type of energy expenditure or energy load associated with them. And then down here is the sludge treatment. So the solids that are collected in the primary and secondary clarifier go to an anaerobic digester, and this is the treatment train for the anaerobic digester. The elements that are shown in dashed boxes are the elements that we added to constitute a microgrid at the wastewater treatment plant. So we put in a flow equalization basin, and this basin, then you can divert raw wastewater into this basin so it doesn't have to go through this treatment train. And in doing that, then it's a way to store water so you don't have to expend energy to treat it. And at some later date, you put it back into the system and then treat it, and then your energy expenditure goes up. So it's a way to shift electric load simply by storing water. Unlike potable water, where you can encourage people not to use it, it's very hard to encourage people not to generate wastewater. But a flow equalization basin is a way for a wastewater treatment plant to help encourage that kind of behavior. We also put on a very large battery on site, and we put in a cogen facility that uses the methane from the anaerobic digester to generate electricity. So these three elements constitute the microgrid that we created on site. So these are schematics of each of these different elements. This is the flow equalization basin. This is the battery bank, and this is the CHP, or combined heat and power. This is the cogen facility. I'll refer to it as the CHP. And this is just a simple representation of the impact that this microgrid had. So shown here is the energy use expressed in megawatts as a function of time over a typical day. Don't worry about this blue bar here, but focus on the green bar. So this green bar is the time in the state of California. So this corresponds to roughly 1 to 3 in the afternoon. This is the time that when the statewide grid has a tremendous, this is the time on the statewide grid when the statewide grid wants to reduce the amount of energy that it needs to provide. So in other words, they want all their customers to use less energy. And shown here in the blue is what the wastewater treatment plant would typically use. And shown in red is their actual energy use by them activating their microgrid. So by activating their microgrid, their net demand onto the grid, onto the statewide electric grid goes down during this time period. And so the microgrid is having the same effect as water demand management in that it is modifying when electricity is pulled off of the statewide electric grid. So it's being very beneficial to the statewide electric grid, but it's achieving it, the microgrid is achieving that reduction of energy that's pulled off the statewide electric grid by generating and storing energy on site. So it's achieving the same outcome as water demand management, but with different means. And I just wanted to put this in as the last example to help illustrate that microgrids can be very effective as well in helping modify energy demand to achieve goals that are stipulated by large-scale electric grids, like at the state or federal level. So with that, I'll stop and I'd be happy to answer questions. I'm sorry for the technical difficulty in the middle of the presentation, but thank you for your patience and thank you for your time. So I will pull up, oops, I'm gonna stop sharing and I'm gonna pull up the chats to see if there's any questions. See, we have about 8 minutes for questions. So let me look through real quick and I will. Hey, Jorgen, could you, for the sake of time, could you identify some questions that are in Spanish? I can read them. I'm very slow at reading Spanish, but I can read it. But for the sake of time, could you identify a few questions to ask and I'll look at the ones in English.
Yes. One question is, what capacity does a wastewater treatment plant have to be in order to be profitable to generate electricity, taking into account that it is for food industry and the COD is between 5,000 and 7,000 ppm.
What capacity does the wastewater treatment plant have to generate electricity?
Yeah.
So, well, with a COD of that value, you're going to have a tremendous capacity to generate electricity. I don't know off the top of my head how many kilowatt hours of electricity you could generate, but I can say with a high degree of confidence that you could generate quite a bit of electricity with a COD value that high. So, yeah, of the three different elements that we put into our microgrid, that again was run as a pilot. So we had a flow equalization basin, we had a battery, and we had a combined heat and power system that basically burned methane. Of those three elements, the CHP unit produced by far the most amount of electricity. And so when you start looking at wastewaters that have very high amounts of organic material, like on the order of 5,000 milligrams per liter of COD, that would translate into a large amount of methane, and that then would translate into a large amount of electricity. So I think that would be a great location to look at this further. So I have another question. Maybe Jorgen, let's alternate, and I can look at some that are in English. So what types of incentives does water utilities use to influence human behavior? Do they pay less for water? And this is a great question. So the biggest incentive, so this idea of incentives is interesting because energy utilities have the ability to create these incentives. So you can create energy utility can create any type of incentive to achieve some sort of goal. And if they're effective incentives, then they will achieve their goal. So in the state of California, energy utilities, the incentives they've created to help motivate water utilities to shift their electric load, what they've done is they've priced electricity for every hour over the course of an entire day, for every day. They have priced electricity to reflect when they want water agencies to shift their electric load and when they don't. So during the hours of 1 to roughly 5 p.m., electricity can be incredibly cheap. And in some cases, it's negative. It's a negative rate, which means you're getting paid to use electricity. Then there's other times of the day when electricity is very expensive, and that's generally between the hours of 6 and 9 p.m. So just by pricing electricity in a very aggressive way, they have been very effective at encouraging water agencies to shift when they use electricity. Water agencies in turn now are exploring different ways to shift that electricity. Water demand management is a fairly new idea that water agencies are beginning to explore as a means to help them save electricity and ultimately the money they spend on electricity. Jorgen, you got another one?
Yeah, there's another one from Gabriela. Does UC Davis plan to collaborate with the state of California to implement these initiatives at the statewide level?
Yeah, so the series of the 4 projects that I have illustrated to you today are have been pilot studies that have been funded by the state of California to collect information that will help inform how they develop policies to roll this out statewide. So yes, the state of California is moving in the direction of doing this. There's some regions of the state that are actually doing this today, and there's other regions of the state that are in the planning phases. But yes, the state of California is moving in the direction of rolling this out statewide.
And there's an additional question from Miguel Angel. Miguel Angel would like to speak. Is it possible, Monica, to make his question?
Okay, can you listen to me?
Yes.
Okay, nice to see you again, Frank. I have some questions, but I don't know if we have enough time to do it, to make these questions. But first of all, I would like to ask you something regarding the first example that you show us. Indeed, I was very surprised that the electricity that is used in water and wastewater system is very high. You mentioned approximately 20%.
Yes.
And you show the strategy to change the human or the customer behaviors during the water consumption during the day in such a way that also you can shift the energy consumption. And you show us the water reports that you can receive in your homes about your water consumption and of course your energy consumption. But I am wondering, is it really easy to change this customer behavior, especially because the daily activities day, I mean, according to the studies of water consumption in homes, normally during the morning and during the evening, the water consumption increases because taking a shower, because the use of toilets, etc. So these kind of changes, I think in a normal society is very difficult to change in such a way that we can change these patterns of water consumption. And also another issue that I am wondering is how easy people can receive these reports in their homes, especially because you need a lot of technology in such a way that all homes can be connected to this technology. I don't know what you can say about that, those kind of issues.
Yeah, so to your first point of you know how much electricity demand can be shifted through water demand management, you're right in that there is a portion of water demand that is just unshiftable. So you know we all use water in the mornings before we go to work, and we use water when we get home from work. And those time periods are very hard to shift in the other times of the day because those other times of the day we're not home. So there certainly is an element here that is unshiftable. And so we have really tackled this problem as two pieces. So one is recognizing that there is a shiftable portion of demand, and how best should we help encourage customers to shift that demand. And the other piece is that water agents, so for that unshiftable demand, water agencies or water utilities themselves can do certain activities to help shift their use of electricity. And the primary activity that they can do is to store water. So if they have the ability, if they have large storage tanks, then they can time the storage of that water to coincide with times when they want to use electricity and when they don't want to use electricity. And if they don't have storage, then we've developed means to help water agencies to begin to understand the cost effectiveness of installing storage. In some cases, it's not cost effective. In other cases, it is. So it's really a two-pronged approach of managing water demand and creating storage within the water utility for the water utility itself to help manage their electric load. But with those two features in place, water utilities can shift a tremendous amount of electric load. But it's not just one activity over the other. And just getting at the unshiftable portion of water demand, while you're right that it's really, there's time periods over a normal work week when you just can't shift water, but on the weekends you have a lot more flexibility. And what we found in California too is that with the integration of renewable energy, the biggest problems we have with curtailment happen on the weekends, not on the weekdays, because the weekdays we have all the businesses that need electricity, and on the weekends they all go away. We still have the same amount of renewable energy, and our ability to shift water demand on the weekends is a lot greater. And then what was your second question? Oh wait, you're on mute again. You go.
Microphone. Okay, the second question was the water reports that people get in homes. How many people can really have access to this connection in such a way that individually everyone can change their behavior in such a way that we can distribute more homogeneously the water consumption and consequently the energy consumption.
Yeah. So we have worked with two primary methods of providing that information. So one is through the web, so right now we have a web portal we've created, but you can imagine you can also have, it's a web portal, but it also has an app on a phone that you can download and use. So you have access to the web, you can get it through a phone. And then for those customers that don't have access to the web or a phone or a data plan of some type, we also have mailed out information through the Postal Service. And we found that all three are effective, but in terms of actually getting customer uptake of the messaging, we found currently that the most effective means is by mailing the information through the Postal Service and not using electronic means. But I mean, for those areas concerned about, social equity, access to the internet, and areas that don't necessarily have, everyone has that, you can use the Postal Service as a means to disseminate that information. And when I say all that, it's still an area of active interest and need is to further explore how to make this information accessible. So I don't want to downplay the importance and need for continued efforts to get this information to the customers. So I have another question that says, how easy or hard is it for power companies and water utilities to collaborate on these strategies? I like this question a lot because I don't want you to leave this webinar thinking that what I've shown to you is, it does require a very close collaboration between water utilities and energy utilities. And I don't want you to leave with the impression that this is easy to do. It's tremendously hard to do. And it's not because people don't want to work together. It's largely because the water sector and the energy sector have historically been siloed. And now we're entering into an era where we're asking them to begin to work together. And it's possible, and we've been successful at it, but it takes a tremendous amount of effort, takes a lot of patience, and it takes some time. But it's largely just an artifact of the fact that these sectors have historically not talked to one another. And now we're asking them not only to talk to one another, but to work very closely together to achieve a common set of goals. And both agencies benefit, but they benefit for different reasons.
Yeah, I don't know if there are any more questions. If there are no more questions, I think we are out of time. It's already 11:06. So I think we come now to the conclusion. And I would like to thank Frank for his conference, for his presentation. Frank demonstrated with his presentation that management of water demand can serve as an effective strategy to conserve water and in turn conserve energy. He showed us new and successful approaches to quantify energy savings, modify customer behavior, irrigation scheduling, and microgrids as a method to shift the timing of electricity use in a water distribution system. I would like to thank all the participants from the different countries, from Mexico, United States of America, Bolivia, France, Guatemala, Panama, Ecuador, Argentina, Peru, Rwanda, and India, and from the different industries, from education, consulting, energy, manufacturing, and real estate industry. We leave our contacts if you have any further questions to the presentations. I also would like to to encourage you to contact us if you are interested about our research programs at Tecnológico de Monterrey regarding water science and technology and the collaboration with the University of California, Davis. Frank, thank you for your presentation. It was very interesting, and all of you have a good day and a good weekend.
Thank you, everyone. Thank you for your time. And I'd be happy to answer any questions. My contact information is on the last slide of the presentation. Thank you.